All right, well, welcome to Second Friday. Hopefully the quiz went well. Do want to just remind you that the next set of homeworks are going to be due Monday night at midnight. So hopefully you guys have been working on that a little bit. With that said, are there any homework problems we'd like to look at? Any questions you guys have? All right, well, hearing none and seeing none, then we're going to go ahead and continue where we were last time and just keep plugging along. So I'm going to go ahead and switch screens, and I will see you in just 1 second. All right, so just to remind you where we were last time, we had gotten to the point now where we were talking about continuity. And continuity is a property of functions. And really, we have this definition. We know that a function is continuous at a point if three things are true. The first is that the function actually exists at that point. You can plug that number in and get something out. Okay, so the function has to exist. The second thing that has to happen is that the limit has to exist at that point, which means as we're getting closer and closer to that point, there is a value that we obtain. And then the third condition is that those two values have to be the same, that the limit is actually equal to the function value. So if all three of those things are true, then we say that the function is continuous at that point. And we can even then extend this to continuous on an interval. We'll say that f of x is continuous on the interval AB if it is continuous at all points in that interval. Okay, so we had gotten here. I had given you this definition, and this is kind of where we had to end. So what I want to do today is I just want to start with, what does this mean? What are we looking at? Like if we draw a graph, how do we know if it's discontinuous? How can we tell what kind of discontinuity we have? Remember, a discontinuity is a place where a function is not continuous. And so that's really the question, is what does this look like and how does this behave? So let's first just talk about problem spots. What are the problems that come up according to these three? Okay, so the first is, what does it mean if the function doesn't exist? Okay, so let's just kind of let's take these in order and just start here with number one. So let's say f of c does not exist, dne. So what does a function look like if it doesn't exist? Okay, well, here are some things we might see. One is we might have a vertical asymptote. So you've seen that, places where functions don't exist that lead to vertical asymptotes. A great example would be something like f of x equals 1 over x. We know that there's a problem with this thing when we plug in 0. So the function's not defined at x equals 0. That would be a place where it's discontinuous. Okay, so sometimes what we're going to see are vertical asymptotes. And those are places of discontinuity. So another thing that can happen if your function doesn't exist is a hole in the graph. And you may remember that there have been some where we've evaluated limits that when we plugged it in, we got 0 over 0. So the function's not defined. But if you draw the graph, it looks totally fine. It just turns out that there's a hole. There's just one little tiny spot Imagine a bullet has just gone through and shot that one piece away. Everything else is fine, but there's just that one location. So in terms of this first condition, that the function exists, these are the things that can happen if the function doesn't exist. Okay, you can have a vertical asymptote or a hole in the graph. All right, so there's that one. What about if the limit doesn't exist? Let me run over here. So we'll go with the limit as x goes to c does not exist. Okay, so for this one, here are some issues we can have with the limit not existing. First, we've seen in terms of limits not existing, we could again have a vertical asymptote. We now say that that has an infinite limit, like that's the words that we use just so that we can describe it a little bit better, but the limit doesn't exist. Okay, so vertical asymptote, same thing. So vertical asymptote is actually a problem for both of those. But some other places we saw that limits don't exist. I'm going to put here jumps. Jumps in the graph. For example, let's say here is a set of axes and there's a function. If this is c, the limit doesn't exist. The limit as we approach c does not exist for that function. So why not? Why doesn't the limit exist here?
Because both points are it's like two y's share the same x.
Okay, so it's not exactly two y's for that because the open circle says there isn't that value down here, but you're kind of on the right track. But Aaliyah, that's kind of the, she just said that it's because it's different from both sides. The one-sided limits are different. Coming from the left and coming from the right, we get different y values. And I think maybe that's also kind of where you were going, Susanna, but it's the one-sided limits are the same. And we know that for a limit to exist, we have to be approaching the same value from both sides. Okay, so here's another issue for the limit not existing is where we have some sort of a jump. And then a third one I'm going to put on here was that weird oscillation. Remember when we did something like sine of 1 over x and it just like bounced back and forth like crazy, right? So any of the times that you might have a limit issue, you're going to have a discontinuity. So the big one I wanted to add in here was the jump. The jump discontinuity is kind of an important one. Okay, so that's the kind of thing that will happen if the second condition is not met. So then what about the third? What about this one where the limit has to equal the function value? So let's think about what that graph would have to look like. Okay, so let's right here, we're going to have the limit does not equal f of c. And what we're going to do is we're going to draw a graph. And let's start with the limit existing. So I'm going to pick a c, and we'll have the limit exist, but I don't want the function to exist there. So let's do something like this, where here is our c. So that open circle just means that there's a point that's been removed. All right, but you can definitely see that the limit exists because as we go to this from either side, we get the same value. But we also need the function to actually exist there, which means there has to be a dot when x equals c. It's just I can't have that dot be at this hole. And so that dot would just have to be somewhere else. So I don't know, something like that. So this is what that kind of discontinuity would look like, where there is a hole in the graph, and then either above or below that hole is a dot for the function. All right, so those are the kinds of discontinuities that we can get. It's going to look something like this. All right, so any of those things happen, the function is not continuous there. It is a discontinuity. But notice that there are really just a handful. There's just a couple of different kinds of discontinuities. There are these, right? The hole with some extra point, the jump, the vertical asymptote, or just a plain old hole in the graph. And so it turns out that discontinuities, we classify them in a couple of different ways. And so I'm going to put here types of discontinuities. And we classify them in two groups: removable. And of course, if we have removable, the other one, non-removable. Gotta love mathematicians. All right, so all of these can be classified as one or the other. So let me just sort of put them into their respective lists, and we'll talk about why, or like what property the removable all have in common. Okay, so if I just kind of go down our list, the first one we ran into was a vertical asymptote. Well, that's one of the non-removable. So let's put that here. I'm getting tired of writing it, so I'm just going to write VA. You may notice that every time I wrote vertical asymptote, the abbreviation got shorter. It's pretty much standard for me, right? So vertical asymptotes are non-removable. The hole in the graph, that one is removable. Vertical asymptote, okay, the jumps. Jumps are non-removable, as are the oscillation. Okay, those are non-removable. Which then leads to that last one, and we'll call that last one, well, we'll just write it as the limit does not equal f of c. So of the 5 types that we kind of saw as we drew them out, this is how we can classify them. So removable or non-removable. All right, so the reason that those first two are what we call removable is this. Think about both of those situations. Let me kind of draw them both here again. So we've got just the hole, right? And the other one is a hole with a dot. So we call these removable because it's super easy to remove that discontinuity. Super easy. All you have to do is basically plug that hole. Or with this one, move that dot down so that it plugs the hole. Basically, mathematically, what that means is that all we have to do to get rid of that discontinuity is define the function differently at x equals c. Right? Like at this one, if I were to just add in all right, well, it's this function, not at c, but at c, we'll call it something else. Number 2 in removable, it just says the limit as x goes to c does not equal f of c. It's the same statement that's down here. And so the same thing with this. If I just redefine this, instead of saying, oh, at f of c, it's equal to this y value, if I were to change the y value, it would now be continuous. These other ones, you can't do that. Like think about a vertical asymptote. There's no way that even if I just defined a value at that point, all it would do is introduce a dot, but the limit still wouldn't exist, right? Same thing with the jumps. The function's already defined there. I already had a solid dot. I can't connect it up. And also the same issue with that oscillation, just because it's bouncing back and forth, the limit doesn't exist. So notice that really removables, those only happen when the limit exists. If the limit exists, it's going to be a removable discontinuity. If the limit doesn't exist, it's non-removable. So visually, I just like to think of, plugging your finger into the hole. Stop the bleeding. If you can do that, it's removable. Otherwise, it's non-removable. All right, so here is the real mathy definition of continuous. Let me give you the non-mathy. All right, now, normally, if we were in class, I would warn you, I'd say, hey, don't tell any of my fellow math teachers that I'm telling you this, because this is like so not mathy that it makes me look bad, right? And that if you did tell them this, I would deny it. I would deny that I said it. Now, I can't really do that now because this is being recorded. Anyone can go and see this. So now there's actually evidence of me saying this. So just realize how far out on the limb I'm going for you folks by putting this video out there. Right? I'm risking my reputation for you. All right, so here's how you can think about it. Very non-mathematical, but takes into account all of this. All right, so here's a really good way to think about discontinuities or continuous functions. All right, so a function is continuous if you can draw it without lifting your pencil. All right, if you don't like pencil, pen, paintbrush, crayon, whatever you're using to draw it. But if you can actually draw it without lifting your pen or your pencil, then it is continuous. Okay, so you see what I'm saying? I mean, it's very non-mathy. You can explain this to like legit a child, right? Go to grade school, say, hey, if you can draw it without lifting your pencil, we call it continuous. Okay, cool, I get that. As opposed to, well, I mean, if the limit exists and the function exists and those values are the same, then we call it continuous. That kid, I mean, just went over their head, right? So very non-mathy, but takes into account all of this, right? Look at the two examples I have drawn right now. So the hole, I'm drawing, and then I have to jump that point, right? I'm coming up and I have to literally pick up my pen, put it back down on the other side and draw it. Same thing with this one, the hole with the dot on it. I'm drawing. I have to lift my pen, come up here, draw that dot, lift my pen and come back down. Vertical asymptote, regardless of which kind it is, whether we're going to plus or minus infinity or whatever, right? But here's a graph of one of these. So I'm drawing it. Okay, now I got to lift my pen so I can come over here and draw it. Or even if it weren't exactly a butterfly, but one of those where it both goes in the same direction, I still have to jump, right? I'm drawing, and then I have to jump over onto the other side and come back down. So I have to lift my pen. Same thing with the jumps, right? If I've got one of these, I'm drawing, lift my pen, keep drawing. right? The crazy oscillation, there's going to have to be some sort of a jump as you get away from that crazy oscillation to not crazy oscillation, right? But it's that same kind of thing. If you can draw without lifting up that pen or pencil, then it's a continuous function. Okay, so it's totally cool to use this as the, well, let's remember how this works, but realize that there is math behind it. There is a definition. Your function has to exist, your limit has to exist, and the function has to equal the limit value. All right, so how we feel about continuity? At least the idea is all right. Might be a little bit more difficult actually proving it mathematically, but hopefully you feel good with the concept or the idea. Yeah, thumbs up. I'm seeing some thumbs up. Cool. All right, so we've got continuity. Well, so what? Well, continuity is going to be kind of important for a lot of theorems coming forward, and a lot of other things we're going to do. One of the big conditions we're going to have on lots of things is that the function must be continuous, because if it's not continuous, then it doesn't behave very well, or you can't trust it to do what you need it to do. Okay, so on its own, we don't really use continuity, right? Continuous is whatever, but it will matter for other things when we prove them. But let me start giving you a list of functions that are continuous versus those that are not continuous. And when I say continuous, I'm implying over the entire real number line. Okay, so we'll just start making a list of functions that you know, and talk about whether they're continuous or discontinuous. All right, so let's start with continuous. So in the chat box, or if you want to yell one out, can anyone tell me a function that's continuous everywhere that you could draw without lifting your pencil?
Sine.
All right, cool. Got a line was said and typed at exactly the same time. That's beautiful. Yeah, so linear functions are great examples, right? Think about a line. Once you start, you never have to lift your pencil. Okay, it doesn't matter what the slope is, right? Whether it's a positive slope or a negative slope or whatever, lines are continuous. How about, oh, I was just about to ask, and then Mariola beat me to it. She said quadratic. What do you guys think? Quadratics, continuous? Well, I mean, think about it. The graph of a quadratic is a parabola. Once you start drawing that parabola, you never have to lift your pencil. And again, it doesn't matter if it's happy, if it's sad, where the vertex is, nothing. Right? So quadratics are continuous. Well, we can even kind of combine all of that. And so one set are polynomials. So no matter what kind of polynomial function you have, linear, quadratic, cubic, quartic, it doesn't matter, degree 300, polynomials are always continuous. They're nice functions. And if you think about it, this is why we know they're continuous. Go back to the definition. The function exists everywhere. Yeah, polynomials, you never have to worry about anything. You can always plug in a number and do your thing. The limit exists everywhere. Well, we actually already saw just the other day that limits, when we were talking about limits, that polynomials, yep, their limits exist. And does the limit actually equal the function value? Yeah, I mean, that's how we evaluate those, is we start by plugging those numbers in, and well, that's the function value that ended up being the limit. So polynomials are beautiful. They are continuous. All right, other functions that are continuous. Can you think of any other ones? So we're gonna have to think a little bit more complicated, seeing we just took out polynomials. All right, so we got a couple of people throwing some stuff in here. Absolute value function, beautiful. That definitely is. So let me put here absolute value. And someone else put sine and cosine. So you think about those graphs, right? So again, absolute value, remember that's the V. once we start drawing it, we're good. Sine and cosine, that's just the waves, right? And waves are just gonna, yeah, once we start drawing it, we keep drawing it. So sine and cosine, good, that's another one. Here are some more. How about exponential functions? Right, think about f of x equals e to the x. That thing is continuous. Right? So there are a lot that are continuous. We might add some more onto this list as we're going along, but those guys are definitely continuous. I'm actually going to put one more on here, and this one you might go, well, but yeah, how about just the good old square root function or radical functions? So think about square root. I'm going to say that that's continuous. And and remember when I started this, I said, yeah, you might go though, yeah, but what's the yeah, but about this one? What might make you think this isn't continuous? Yeah, so it doesn't go past the origin. It doesn't extend forever left and right, right? Well, this one, the radical function, since it just doesn't even exist out over there, basically anywhere I can draw it, it is continuous. I'm going to put at least on this radical function, I'm going to say on their domain. So as long as we're in the domain of that radical function, we're going to be continuous. And some of them, like a cubic, that one actually does go from minus infinity out to infinity. And so is continuous over the entire real number line. But the radical function works well. Okay, so there are some that are continuous. So let's go to discontinuous. All right, so let's start with something like butterfly function. So I'll put butterfly functions. So for example, 1 over x, because it's got the vertical asymptote. And there are all, and we can shift that around and move it and all that. And so butterfly functions are definitely one of those that have discontinuities. What else? Can you think of other things that are discontinuous? All right, so Bailey just put up step functions. Okay, I love that. I'm going to call it something different though. I'm going to put piecewise defined functions. But step functions is a good way to think about it. So a step function is one of those where it's like, we've got whatever rule for a while, and then after that, we switch to a different rule. Now, I am going to have, I do want to put a little note on this though, for piecewise defined functions. I am going to put in parentheses here though, not all. Right? Some piecewise defined functions are totally fine because they're defined in such a way that these pieces stick together. So you don't actually have to jump from one to the next. Right? But step functions are definitely an example of this. I just kind of wanted to go a little bit broader, Bailey. Let's see, Aaliyah just put in the chat room, the chat box, tangent. Totally. And in fact, not just tangent, but also cotangent, also secant and cosecant. Those guys are all discontinuous. They have all sorts of vertical asymptotes. Let's see. Ooh, how about this one? Because we haven't classified this one anywhere. What about log? Like what about logarithmic functions, like natural log? What do you think? Which one does it kind of fit more in, continuous or discontinuous? Okay, good. So Bailey just said, isn't it just an exponential? Yeah, I mean, yeah, it's logs are exponents backwards, but they are different. I mean, they are different functions because they're the inverse of exponentials. But by that argument, then Bailey, are you saying that it should belong over in the continuous since exponential was over here? Yeah, okay. How the rest of you feel? Does that sound good? Well, let me offer this up. Logarithmic functions have a vertical asymptote. They've got that vertical asymptote at 0. So now what do you think? Continuous, discontinuous? All right, so Bailey is now convinced that it's actually discontinuous. You guys good with that? All right, Susanna's saying continuous. I guess I wasn't able to convince her with vertical asymptote. Well, okay, so here's where I'm going to put that. I am actually going to put it on the continuous list. But I'm going to put exactly the same note that I put with the radical functions. I'm going to put here on the domain. Because logarithms, again, don't go forever from minus infinity to infinity, but wherever they start, as soon as we start drawing it, we never pick up our pen or a pencil. Okay, so it's going to actually be on their domain. We're good. So if all we're talking about is continuous over, like if I just say, okay, here is the set of real numbers, or where is this function continuous? Something like natural log, you'd say, well, this is continuous from 0 to infinity. Happens that the domain is also 0 to infinity, but it is continuous everywhere in there. Okay, so we can start classifying every function you've ever seen as either continuous or discontinuous. And if you run into a situation like these, like the square root function or the natural log, if they are continuous everywhere that they exist, we still go ahead and say they're continuous, right? Because there isn't a jump. We're not jumping over that asymptote. That asymptote's just telling us where to start, basically. So it's a little bit different than like a butterfly function where we're approaching it on one side and then have to jump onto the other side. All right. So that's kind of the difference there. Now, I do want to talk about the butterfly functions because those are a subset of what we call rational functions. And rational functions are those that have fractions on top and on bottom. And rational functions are actually really nice because they're also continuous on their domain. So I'm going to put here rational functions. Just remember rational, this means fraction. So fractional functions. And these are also continuous on their domain. Now, this one, though, there will be jumps over those asymptotes sometimes, like with the butterfly function. But I like to think of it more as a continuous function, except for a couple of places. Similarly with the trigs, those things are continuous, except for a couple of bad spots. And those couple of bad spots are the domain issues. Right. So really what I'm trying to do is help you start seeing how to tell if they're continuous or not because of the fact that it's going to be really useful later. All right, so continuity. Well, let me give you a theorem here. This is going to be your first theorem that there are going to be a whole bunch of theorems that we're going to kind of put together to help us get to the first piece of calculus. And this one is called the intermediate value theorem. Okay. So from henceforth, though, when I write it, it's going to be IVT. So intermediate value theorem. So if you ever see me write IVT, talking about this theorem right here. Okay, so intermediate value theorem says, all right, first of all, here's the condition that we need. Suppose that f of x is continuous on the interval a to b. So notice that this is a closed interval because it's got the brackets, meaning that we do include a and b. Okay, so this is the only condition that we need, is that f of x is continuous. All right, so we've got a continuous function. And let's just say, for the sake of argument, that f of a is less than or equal to f of b. Now, I am going to just tell you that this statement right here, it could also be the other direction. It doesn't really matter. I'm just picking one so that we can run with it, so that we can actually draw it and see what's going on. But I'll show you how if we switch it, it doesn't really change anything. Okay, so then what this says is, then given, say, a y that's somewhere between f of a and f of b, there exists a c that's somewhere between a and b, such that f of c equals that y. So I'll give you a second to write that down, and then I'll help you like translate that into regular speak. All right, so what the hell does this actually mean? Let me actually draw a picture, because I think the picture definitely helps you see what's going on. So we've got our axes. We've got our function. And somewhere over here is A. Let's just say that this is A, and somewhere over here is B. So there are dots on this graph. If we run over onto the y-axis for both of them, this lower one is f of A, and this higher one is f of B. Okay, so here's what we got. It's a continuous function, right? I didn't lift my pencil in between A and B. And I've got that f of A is below f of B. Okay, so conditions are met. Now, notice what this is. So now you give me a y that's somewhere between A and B, or between f of A and f of B. So how about this one right here? There's y. What the intermediate value theorem tells me is that there's going to be somewhere between A and B such that when I plug it in, I get the value y. Well, on my graph, here's a point that has that y value. This is that guy, C. So this theorem just says that given any value in between those, I'm going to find somewhere in this interval where I get that same y value. So what if we were to like lower it, let's say, or go higher or something like that? So let's say we get a smaller y, go with this black one. Well, that's a different C, but that C is still somewhere in our interval. So this is called the intermediate value theorem because it says that given any value that's in between these, any intermediate value, you can find a point that's somewhere between these, something that's intermediate, that gives us that value. But the most important piece of this is that it must be continuous. Because if it's not continuous, this isn't a guarantee. Let me show you an example of that. All right, so here's an example of a function that's discontinuous and such that we can't find those intermediate values. All right, so let's say we're coming up like this. All right, so there's a discontinuous function. Let me give you an A and a B. So here's A, here's B. So if we run across horizontally, there's f of B and here's f of A. So maybe this is enough for you to see why the intermediate value theorem is not going to work. But let me just be real explicit here. Let's choose a y value that's between f of A and f of B. Right here. Find me a point on the graph of that blue, where the y value is equal to where that red line is. Well, I'll even make this a dashed line so you can see it all. So the question is, where does our graph actually cross that line? And the answer is nowhere, right? It doesn't. So this is a situation where the intermediate value theorem, where you might go, oh, the intermediate value theorem isn't actually true. But that's not correct. I mean, the issue is that it's not continuous. So as soon as you have a discontinuity, you may still be able to do this. You may not. You're just not guaranteed. If it's continuous, guaranteed, 100%, you will be able to find somewhere in that interval where you get that y value. Okay, so that's why it's super important that continuity exists. Without it being continuous, there's no guarantee. Let me also show you why this inequality can actually go the other direction and doesn't really matter. I'm sure it's not a big surprise to you. But let's say it was turned around so that the left point was higher than the right point. So there's a continuous function from A to B. So here's A, here's B. So there's f of A and f of B. But still, no matter what, you give me any value in between those, somewhere my graph is crossing that line in this interval. So the greater than or equal, less than or equal, that doesn't really matter. If they are equal, it's kind of silly because there are no intermediate values, right? But for either of these cases, it's totally fine as long as we're continuous. All right, now I want to show you one other thing that sometimes students think is a problem, but it isn't. And that's a situation like this. Let's take a function. We'll make it a polynomial of some type. It's got some turnaround points. So something like that. And just to have an interval here, let's say that this is A and this is B. So if we look at those 2 points and run them across, here's f of A and here's f of B. Now, it is continuous. It's polynomial, right? We're able to draw it without lifting our pencil, so that thing is continuous. So the intermediate value theorem should apply. So let's pick a y that's somewhere between f of A and f of B, say this one right here. And notice that if we were to go across on that y, we have a whole bunch of points where it intersects. Let me mark them on the x-axis here. So we had this one, this one, this one, and this one. So first of all, see this last one is not between A and B. It's not in the interval. If you run into that, that's not a problem. This theorem doesn't say anything that those points are only between A and B. It just says that there will be one between A and B. Right? That one exists between A and B. So there can be others outside of that interval, and I don't care. Doesn't matter. We're not concerned about those. Okay. So if you run into that, don't freak out. It's fine. Something outside the interval, no big deal. There just has to be something inside the interval where this happens. Okay, now, in this case, here's the other issue sometimes people have, is they go, right, but if you look at it, there's 1, 2, 3 places between A and B where we get that y value. Okay, yeah, so more than one. Again, not a problem, right? Because all this says is that there exists a place in there. It doesn't say only one place. Right? There's a difference between saying something exists and something only exists. So there's a big logical difference. And if you don't think that that matters, you should look at what's going on in the news these days, because there's a simple statement out there. Black Lives Matter. And even me saying that right now may have triggered some of you because it has become such a big thing, right? So if I say Black Lives Matter, doesn't mean non-Black Lives Matter. I'm just saying Black Lives Matter. Not only Black Lives Matter, right? So the same kind of thing here. If I say C exists, I'm not saying only that C. I'm saying just that C. So you can see how just one word difference can create major issues. Now, I know comparing math to the state of the world is probably a little, but it really shows you how logic statement, logical statements, the wording is very important, right? And so we'll do that in math. Like if I want to say there's only one, I will say that. We'll use words like there is a unique value. There is only one value, right? But in the absence of that, if all I'm saying is there is a place, okay, there is a place. There's 3 of them. Okay, cool. There's still a place. There's just more than one. All right, so just realize that when we make a statement like this, there can be more than one unless we specify it. So if you run into this and where you go, well, there's more than one C in there, okay, that's fine. This is just guaranteeing that there is one. The extras are bonuses. Or maybe we want to know those as well. Now, this theorem, believe it or not, you've used it before. You may not realize it because it's never been like stated to you before as the intermediate value theorem. But let me show you an example of where you've done this. If you came through our classes, this was Math 103A, the first pre-calculus class. So if you went, if you came from a different school or you had this in high school or wherever, this is somewhere in algebra, you run into this. But you remember things like, for example, find all zeros of f of x equals 3x cubed minus 2x squared plus x plus 4. Yeah, let's make that minus 4. So you remember this kind of problem, I'm sure. So another way of thinking about this, finding all zeros, means find all x-intercepts and all that. And so you have all kinds of theorems and things that you can use to try to find them. But when all else fails, you do something like this. You go, okay, well, let's see. What happens if I plug in 1? We're just going to see if we can find a 0. So if I plug in 1, I get 3 minus 2 plus 1 minus 4, which is negative 2. Okay, well, now let me plug in 2. Well, that's going to give me 3 times 8, which is 24, minus 4 times 2, which is 8, plus 2 minus 4, which gives me, I think that's 14. And at this point, you went, oh, wait a minute. We went from a negative to a positive, which means that somewhere between 1 and 2 is a root, right? So then maybe you might try, well, let me try 1.5. If that's positive, then I know the root is between 1 and 1.5. If it's negative, I know that root is between 1.5 and 2, right? But it basically gave you an idea of where to look. So you kind of remember doing that? The whole, oh, one's positive, the other's negative, so I'm somewhere in between. That's intermediate value theorem. Check it out. It's a polynomial, it's continuous. All right, so it's a continuous function. Here are a and b, 1 and 2. F of a is less than f of b. I want a number somewhere between negative 2 and 14, specifically the number 0. Well, I'm guaranteed somewhere between 1 and 2 where that 0 exists. So anytime you've done one of those kinds of things, and it's not just this. If you've ever tried to like find a square root of a number this way, right? Square root of 2. Well, 1 squared is 1, 2 squared is 4, so it's somewhere between 1 and 2. Let's try 1.5. 1.5 squared, 2.25. Ooh, that's too big. I need to go smaller. So anytime you've done one of those like search and destroy kind of methods, you're using an intermediate value theorem. You just didn't know it, right? So it's not new. We're just specifically stating. All right, I think I'm going to call it right now. We're really close to our time. I definitely don't want to start the next topic. So just so you guys know, we're almost done with chapter 2. There's one more section we need to talk about, and we're going to talk a little bit more about limits, how mathematicians actually define them. Because this whole idea of close, that's not very mathy, right? Like when we talk about limits, what happens as we get close to C? No, mathematicians don't like that. We want to define things. So I'm going to introduce you the way that mathematicians really define limits. And then after that, we'll start getting into derivatives. We'll start actually doing calculus because we'll have set the table for everything. All right, so just a real quick reminder, don't forget the next set of homeworks are due Monday night at midnight, so get in there and work on it. Of course, on Monday, if you have questions, we can talk about them in class, and I am available always through email or messaging. But other than that, I hope you guys have an awesome weekend, and I will see everybody on Monday. See ya.
Thank you.
Peace.
Hey, Bruce. Can we go over the scanning thing?